Welcome to this explainer. When most of us think of math, we usually picture endless equations, right? Just crunching numbers to find that one exact answer. But today, we are diving into a whole other world of mathematics. Honestly, it feels a lot less like algebra and a lot more like magic. We're going to explore how mathematicians prove that certain things absolutely must exist, even in complete chaos, without ever actually finding them. To really set the stage here, picture this legendary and frankly hilarious scenario from the brilliant Hungarian mathematician Paul Erdős. He once proposed this thought experiment where super intelligent aliens invade Earth, and they threaten to completely destroy us unless humanity can calculate this specific, highly complex mathematical value known as the Ramsey number for 5 and 5. Erdős said, well, if we marshal the world's best minds and our absolute fastest supercomputers, we could probably figure it out and save the world. But what if those same aliens demanded the Ramsey number for 6 and 6? Well, according to Erdős, the math gets so impossibly complex at that point that our only real option would be to launch a preemptive military attack. I know, it sounds totally crazy, right? But as we build up our mathematical toolkit today, we're going to uncover exactly why that number is so terrifying. Let's kick things off with a seemingly impossible real-world riddle. Imagine you walk into a party. There are n number of people in the room. Could be 10 people, could be 1,000, doesn't matter. Here's the question. Do two people at this party always know the exact same number of other people there? Think about how chaotic a party is. You've got extreme extroverts chatting up everyone, and you've got wallflowers who don't know a single soul. Without surveying a single person, can you mathematically guarantee that a matching pair exists? Believe it or not, the answer is yes. And we prove it using our very first tool, the Pigeonhole Principle. It sounds incredibly basic. Basically, if you have more pigeons than you have pigeonholes, and every pigeon flies into a hole, well, at least one hole has to contain more than one pigeon. Simple, right? But how does this solve our party problem? Okay, if there are n people, the number of people anyone can know ranges from 0 to n minus 1. But here's the catch, the trick to the whole thing. You literally cannot have someone who knows everyone at the party simultaneously with someone who knows no one. It's impossible. So you actually only have n minus 1 possible degrees of friendship for those n people. Because you have more people, which are our pigeons, than possible friendship numbers, our holes, two people absolutely must share the same number of friends. It's totally guaranteed. Now, what's really interesting about this slide is just how far this seemingly simple principle gets stretched in university-level math. It's a real workhorse. Take an undergrad population of, say, 4,528 students. Since there are only 366 possible birthdays in a leap year, the Pigeonhole Principle mathematically guarantees at least 13 students share the exact same birthday. No question about it. It also proves things like guaranteed equal remainders in division, or that if you take any 30 random 7-digit numbers, there are guaranteed to be two distinct subsets that add up to the exact same sum. And it can even force integers into pairs where one divides the other. The craziest part, the principle doesn't tell us what those numbers are. It just proves, beyond a shadow of a doubt, that they absolutely must exist. But while the Pigeonhole Principle is great at proving something exists, it doesn't tell us exactly how many exist. And mathematicians, well, they want the exact details. To get exact numbers for complex structures, rather than just settling for rough approximations from what's called asymptotic enumeration, mathematicians rely on algebraic enumeration. They don't just want a ballpark figure if they can avoid it. They want the precise, exact formula. And to overcome the limitations of just estimating, they pull two more fundamental tools out of their toolkit. The first of those tools is the elegant art of bijection. Think of a bijection as basically a perfect one-to-one translation between two entirely different sets. If you compare every single item in set A with exactly one item in set B, with absolutely nothing left over, boom, you've proven they have the exact same number of elements. Mathematicians use this trick to count incredibly complicated things, like the number of ways to build a branching tree structure out of nodes, just by translating them into simple, manageable lists of numbers. By finding a bijection, you can count the seemingly impossible without actually having to crunch the raw exhaustive numbers. The next tool up is the generating function, and this brilliantly illustrates a concept using a very accessible metaphor from mathematician Herbert Wilf. He described a generating function as a clothesline on which we hang a sequence of numbers up for display. I love that. Instead of just staring blankly at an infinite sequence of numbers, we assign each number a weight, kind of like a variable x, and we compress that entire infinite sequence into a single, elegant algebraic expression. It's a massive shortcut. This lets mathematicians actually manipulate infinitely long sequences of data using just basic algebra and calculus. Okay, so let's see how all of this builds into an even deeper mystery. We're going to pivot to a brand new, relatable scenario. Imagine another party, but this time, suppose you have a room of exactly 6 people. Is it mathematically guaranteed that you will find either a group of 3 mutual friends or a group of 3 complete mutual strangers? Unlike our pigeonhole example from earlier, we aren't just counting connections anymore. We are now looking for specific, highly complex relationships hidden inside a network. Well, the answer here actually comes from Ramsey theory, and Ramsey theory is based on a really profound idea. Complete disorder is mathematically impossible. Let that sink in. If a system gets large enough, a well-organized subsystem has to emerge. It's like uncovering a secret baked-in rule of the universe. In graph theory, we usually represent people as dots and their friendships as connecting lines. Ramsey theory confidently proves that for a group of 6 people, the answer to our party question is a resounding yes. You are completely guaranteed to find either a triangle of friends or a triangle of strangers. Mathematicians express this elegant little truth by stating that the Ramsey number R3, 3 equals 6. But hold on, why exactly 6? Why wouldn't 5 be enough? Well, imagine 5 dots representing 5 people. If you trace the connection lines, let's say red means friends and blue means strangers, you can actually arrange them to form a red pentagon on the outside and a blue star on the inside. It's a fascinating setup because no matter where you look in that specific web, you will not find a red triangle, and you will not find a blue triangle. It is a perfectly balanced network that completely dodges the rule. This beautifully, visually proves why 5 people is simply not enough to guarantee order. You absolutely positively need that 6th person to tip the scales and force the pattern to emerge. Which brings us right back to our alien invasion. Think about it. If R33 is 6, what happens when we scale this up? Well, R44 has been proven to be 18. Okay, manageable. But R55? We actually don't know the exact answer. We only know it sits somewhere between 43 and 49. The combinatorial possibilities explode so violently that absolutely no computer on Earth can check all the variations of friendships and strangers for just 43 people. And R66? That is exactly why Erdős joked about the preemptive military strike. The sheer number of possible networks for 6 and 6 is so unimaginably vast that trying to calculate it by brute force is literally beyond the physical limits of our universe. So you can see how this leaves mathematicians with a massive, massive problem. If the combinations are just too vast for even our greatest supercomputers, how on earth do we prove that certain mathematical structures or boundaries exist? I mean, how do you prove something is there if you literally cannot find it, calculate it, or explicitly build a model of it? So the crucial point is this exact dilemma is what brings us to our final and perhaps most magical tool of all, the probabilistic method. Pioneered by Paul Erdős himself, the logic here is astonishingly simple, yet incredibly powerful. It goes like this. If you can prove that the probability of randomly generating a structure with your desired properties is strictly greater than 0, then that structure absolutely must exist. No way around it. You don't have to build it. You don't have to painstakingly find it. You just metaphorically roll the mathematical dice, calculate the averages, and if the chance of success isn't exactly 0, reality dictates that the object is out there somewhere in the mathematical universe. Erdős actually used this very method to solve seemingly impossible problems in graph theory. A great example of the weirdness we are talking about is something called the Grits graph. It has absolutely no triangles, meaning no immediate clusters of 3. Yet it inherently requires 4 different colors so that no 2 connected dots share the same color. Using his probabilistic method, Erdős proved that there are graphs out there with arbitrarily massive loops and 0 short clusters that still require an infinitely large number of colors to complete. He didn't draw these graphs, right? They are way too complex for that. He simply proved that if you randomly connect dots under certain probabilities, the chance of creating one of these paradoxical graphs is greater than 0. Therefore, they exist. From the simple Pigeonhole Principle mapping out birthday twins, all the way to Ramsey theory proving that total absolute chaos is a mathematical impossibility, we've seen how these tools pull guaranteed order right out of the void. And honestly, it leaves us with such a fascinating thought to end on today. If mathematicians can prove that a party of 6 people will always contain a guaranteed pattern of relationships, if they can prove that complete disorder is structurally impossible in our universe, well, how much of the random chaos in your own life is actually just a vast, invisible, mathematically guaranteed pattern waiting to be discovered? Thanks so much for joining me on this explainer, and hey, keep looking for those patterns.